Good morning. My name is Craig Prater. I'm the Chief Technology Officer of Nanoscale Instruments, and I'll be the moderator for today's webinar. I want to welcome you to our special presentation by Dr. Gregory Myers from the Dow Chemical Company entitled Nanoscale IR Spectroscopy, or AFM IR, Achieving Molecular Understanding of Polymer Systems. With that, I'd like to give a brief introduction to what we'll be talking about today. So I will start out. I'm going to give you an introduction to Nanoscale Instruments, a little bit about our background, and then I'm going to talk about some Nanoscale Instruments products and technology, including specifically I'll introduce the AFM-based infrared spectroscopy, this AFM IR, that then Greg will talk about in much more detail. And then I'm going to also talk very briefly about a complementary technique called scattering scanning near-field optical microscopy, or SNOM. And then I will talk about a couple of complementary techniques for nanoscale thermal analysis and nanomechanical spectroscopy. And then I will turn it over to our main speaker for today, Dr. Greg Myers from Dow Chemical, and he'll talk about this nanoscale IR spectroscopy, or AFM IR, achieving molecular understanding of polymer systems. So let me start out with a little bit of motivation. Why should you hopefully be interested in this talk today? So nanoscale infrared spectroscopy has the following key benefits. First of all, it provides nanoscale chemical analysis in combination with measurements on an atomic force microscope. So you can take an atomic force microscope image, click anywhere on that image, and get infrared absorption spectra to help you analyze the chemical makeup of your sample. These spectra are highly analogous to FTIR, conventional infrared spectroscopy, and so you can apply the same type of interpretation that you would to conventional infrared spectra. We can also tune our laser source to any individual absorption peak and then do chemical composition mapping to visualize the distribution of different chemical species in biological and other samples. And the sensitivity of this technique, as I'll show you, can go down to the scale of single monolayers. So it has applications for very small samples, proteins, membranes, things like that. This technique has also proved to be very productive in terms of the scientific discovery, and I'll show you later. There's lots and lots of publications on our website. We have just released our third generation of nanoscale spectroscopy platform, the NanoIR 2S, and we're really proud of the awards that we've been recognized with for the technology and product innovations, and also quite a number of patents that we've received for these innovations. But just briefly, these two techniques, the AFM IR technique, which we'll be talking about mostly today, is a photothermal technique where we illuminate the sample with infrared radiation from a tunable laser, and when that light is absorbed, it causes a thermal expansion of the sample, and that thermal expansion is directly proportional to the absorption coefficient. And I'll show you this in more detail in just a moment. The SNOM technique, by comparison, instead of measuring thermal expansion, it measures the light that's scattered from the tip sample region. These two techniques are highly complementary. The AFM IR technique, as I said, is very analogous to conventional FTIR, so it's great for measuring, getting direct measurements of the IR absorption spectra and doing chemical imaging, especially on soft samples, whereas the SNOM technique is more analogous to ellipsometry, excellent technique for nanoscale imaging of optical properties, and especially for inorganics and hard materials. This is what a NanoIR 2S looks like. It comprises the AFM unit where the sample is measured. There is support for multiple laser sources if desired, the ability to rotate the polarization of the incoming beam for orientation studies, to support this SNOM capability, there is a microfilm interferometer and infrared detector right here. So now I'd like to just introduce the technique that we're going to focus on today, this AFM-based infrared spectroscopy, or AFM-IR. You'll hear a little bit more about the development of this later in Greg's portion of the talk, but it was developed originally by Alex Dazzi, who was recognized in 2014 with the Ernst Abbe Award for his innovation there. The basic idea is that we have a pulsed tunable infrared light source that is focused onto a sample in the region of the AFM tip. And if we tune the the wavelength of this IR laser source to an absorbing band of the sample, what happens is a portion of that light is absorbed by the sample and turns into heat. That heat causes a rapid thermal expansion of the sample that causes the cantilever to oscillate, and then we measure that oscillation amplitude, which is indicative of the amount of IR absorption. I'll show you that in a little bit more detail in just a moment. And then a really nice thing about this AFM-IR technique is that it correlates very well to conventional FTIR, as I said, because it's measuring the same fundamental property, the absorption of IR light. And so because of that, you can use the same sort of analysis techniques to look at AFM-IR spectra, to look at the relative peak heights, to look at the peak positions, et cetera, to look at the pattern of peaks as a fingerprint, to identify unknown materials, for example. We start out with an optical image, find a region that we want to scan. We scan it in a conventional way with the AFM tip, creating an AFM image. And then from the AFM image, we're going to pick a region where we want to do a spectroscopic measurement. So we're going to bring the tip down to the sample surface and start illuminating the sample with pulses of infrared light. And if we've tuned to a wavelength where the sample absorbs, we will start exciting these molecules, exciting the molecular bonds in those molecules, and that absorbed light turns into heat that causes a thermal expansion that pushes up on the tip of the AFM. So now what we do is we record the oscillation of the cantilever as a function of wavelength, or a function of wave number, as we're sending in these pulses of light. And then we can create an absorption spectrum simply by tracing the envelope of this of these cantilever oscillations as a function of wave number. And then each one of these peaks corresponds to a specific molecular vibration. The pattern of peaks acts as a fingerprint. So we can then repeat this at any arbitrary location in the AFM image and then get chemically resolved spectroscopic analysis. All right, so the typical workflow, and Greg will talk more about this, is basically you collect an AFM image, you can program some series of spectra, you can then acquire those spectra automatically, identify the key peaks that distinguish the different materials, and then you can tune the laser to any specific wavelength. We use narrow band laser sources so that you can tune to any absorbing band and then collect an absorption image, and Greg will show you a number of examples of this. And you can make ratiometric images where you compare the ratio of absorption at one peak versus another peak, and then make nanoscale composition maps based on that. Another capability we have is to do complementary mechanical property imaging, and basically what we can do is measure the, in addition to measuring the oscillation amplitude, we can measure the oscillation frequency, and that frequency shifts depending on the elasticity of the sample. So we get a complementary measurement of topography, elasticity, and then also this chemical capabilities. We also recently, in collaboration with Mikhail Belkin at the University of Texas, developed a technique called resonance-enhanced AFM IR, where we synchronously pulse the laser with the contact resonance frequency of the cantilever, and that lets us achieve very, very high sensitivity, including that monolayer sensitivity that I mentioned earlier. Just very briefly, a couple of final complementary measurement techniques. I mentioned this one earlier, this nanothermal analysis, where we can use a heated AFM tip to locally ramp the temperature of the sample right underneath the probe apex, and we can measure softening temperatures like glass transition temperatures and melting temperatures. And then we have a wideband nanomechanical spectroscopy technique called Lorentz contact resonance that lets us map the sample stiffness. We can take mechanical spectra and also get mechanical stiffness and damping images. There are a very large number of publications using the AFM IR technique up on our website, and so if you're interested to learn more, please check out our website, anasysinstruments.com, under the Publications tab. And also, as I mentioned, there are a large number of pre-recorded webinars on a variety of topics that you can peruse if you're interested in more details. So with that, I'd like to hand things over to my friend and longtime collaborator, Greg Myers at Dow. So Greg is a fellow in core R&D, analytical sciences at the Dow Chemical Company. He has technical leadership for strategic planning within the surface and interface characterization group there at Dow. He's won numerous awards for his contributions to the field of scanning probe microscopy, and pioneered a lot of those techniques for industrial R&D. We had the pleasure of working together on a NIST ATP project focused on quantitative nanomechanical measurements with AFM, and Greg was also instrumental in the original development of our Nano-IR platform and was a co-recipient of the 2010 R&D 100 Award winner for his participation in that. Greg's the co-author of one textbook, 3 book chapters, 50 publications, and 2 patents, and has a PhD in inorganic chemistry from Texas A&M, where we happened to overlap, though we didn't know each other back then. All right, with that, I'm going to now hand the presentation over for Greg. If you...
Well, thanks so much, Craig, and I appreciate the kind introduction and the introduction to the technique. It's a pleasure, and thank Anasys, of course, for sponsoring this webinar today. Good morning to everybody. So today I'd like to describe this relatively new capability that allows us now to image or map chemical functionality at the nanoscale in polymeric systems. It focuses really this technique on the rich information content that's available through vibrational spectroscopy, which for many of you, I can appreciate it's been a workhorse bulk technique for characterizing polymeric materials and systems. Before I get started, I'd like to just quickly acknowledge my coworkers at Dow Chemical who have helped me in this work. It's Dr. Mark Rickard, Carl Reinhardt, and Jamie Stanley. So as with any optical technique, infrared spectroscopy is spatially limited due to diffraction, and that's shown at the top by the ABI criteria, for spatial resolution in a diffraction-limited optical system. And so theoretically, this limit depends both on the wavelength in the numerator and the refractive index of the numerical aperture related to the refractive index of the optics. And so for this region in the mid-IR, spatial resolution is going to be limited, and it will be variable. So this table kind of attempts to give you an appreciation for that. In conventional IR transmission microscopy, that in the mid-IR, that resolution would be about 10 to 30 microns laterally. ATR is a little bit better, primarily because we're using higher refractive index optics with the ATR crystal. That improves that maybe by a factor of 3. Confocal Raman microscopy gets us better resolutions further because we're using a shorter wavelength of light in the source radiation for scattering, and we have confocal optics in that path. But clearly nothing is there that gets us where we want to be in the nanoscale. That is, there's a significant gap for accessible sub-100 nanometer vibrational analysis. Now, in contrast, atomic force microscopy readily gives us nanoscale resolution. We have well-controlled force of a nanometer-sized tip in contact with the surface that we're studying. There's lots of methods to see material contrast in many modes of AFM operation. Several are listed here that get us mechanically mediated mapping or adhesive, electrical, and thermal property analysis, even those that Craig alluded to earlier from ANSYS. Selective chemical functionality and mapping can be done in a molecular recognition system, but that requires us to chemically functionalize the tip or the sample. So we kind of have to know ahead of time what we're going after in order to make that successful. But we have no broadly applicable chemical characterization method until recently that's based on an AFM. So it's an obvious marriage of kind of these two techniques. Now at Dow in the last few years, we've kind of had an internal development program to characterize chemical functional structure at nanoscales, and spectroscopic mapping at these scales. It's possible using some of the methods shown in this table. For example, in the electron microscope, we can use electron energy loss spectroscopy at high spatial resolution. One could go to a synchrotron using X-ray absorption spectroscopy to get very highly resolved spectral information. But the last 5 years have seen commercialization of some of these AFM-mediated techniques that bring vibrational spectroscopy beyond the diffraction limit, and those are in the red box shown here. Of course, the one I'm going to be talking about today is photothermal induced resonance, or AFM-IR. Two other scattering-based methods, elastically scattered light, that Craig alluded to, is the near-field optical microscopy that is also sold by ANSYS in their newer system. And a third method is tip-enhanced Raman inelastic scattering from a metal tip. But today I'm going to describe our success with the AFM-IR method. So Craig nicely talked about the AFM-IR method, so as I get to that, I'm going to give you a little bit more about the development history. I'd like to give you some validation experiments that help us peg the spatial resolution of this methodology. This was really important to us. We wanted to see that this thing operates as advertised, sub-100 nanometer, and we'll talk about that. And then we'll go into some specific sample applications that cover many different polymer material systems for many different material industries, and then wrap up with a brief conclusion. So the AFM-IR was developed by ANSYS and commercialized by ANSYS. And that was facilitated by, of course, several strategic and key collaborations during its development. Many of the participants, of course, are listed here. An important aspect of this work was the early incorporation of potential material suppliers and end users of the technology that represents a lot of and a wide variety of industries, polymeric materials, automotive, semiconductor as examples. And the work was, of course, supported by government financing through NIST and ATP programs. Craig gave you a nice snapshot of how the technique works. This is an early cartoon I had from him during our collaboration. I'll run this really quickly. We have, in this case, this is the original implementation of the technique using a single bounce ATR crystal, and in this case, the pulsed mid-IR radiation came from below the sample and was reflected internally into the crystal, excited the sample. Where there was absorption, we got the resonance as shown before, and the ring down shown up here on the right. Craig talked about Alexander as being the founder of the technique, several of his publications shown in the bottom left here. And another key developer in the technology was Professor Konstantin Vodopianov at Stanford, who helped develop benchtop sources for the technique. So the current implementation, the one that we've have installed here at Dow, is the second generation instrument, and as Craig showed, it's top-down radiation of the IR. This essentially opens up the sample possibilities much more broadly with easy access from the top. and to a wider variety perhaps of sample types. Here are several of the key characteristics of the system, and then the picture in the middle showing the laser at the back, the steering optics here, and then the AFM is at the front of the system. And again, showing you the ring down due to absorption. It's with Fourier analysis converted to its amplitude and frequency components that can be tracked as a function of wave number, generating an infrared spectrum where there's no absorption, there's no kick to the lever, so no signal. Where there's strong absorption, there's a strong ring down and a larger signal to noise at that point. So let's get into some details about the our experimental protocols. Generally, for the samples we're looking at, we use microtomy techniques. We still like to use sections, even though we have top-down optics, and the optimum section thickness is typically around 300 nanometers. We're well practiced at doing this at Dow. And this is either by cryo or room temperature microtomy methods. The sections are placed on either IR reflective or transparent supports. And I'll show you one example where we had a hybrid system we made that contained both organic and inorganic materials that were prepared on a silicon wafer substrate that's damaging to the knife. We couldn't microtome that sample, so instead we used focused ion beam milling as a method to prepare it and pluck a section and then turn it on its side for analysis. Since we're relying on the photothermal effect, that is the kicking or ringing of the cantilever, it helps if the cantilever spring is fairly soft and weak, and so these are low spring constant cantilevers for those of you who are practiced in the AFM methodology. They're also gold coated to minimize non-selective infrared absorption. They're metal coated probes. And this is on the lower right-hand side here is a reconstructed image of one of these probes with about a 40 nanometer radius at the outer apex, just to give you an idea of its shape. One of the things we really enjoy about the nano-IR capability, AFM-IR, is that the raw image maps are rendered without really any need to do any post-processing, and they're fairly straightforward to interpret. The height imaging that I'll show you may have been flattened to remove artifacts or leveling. So let's talk about spatial resolution. This again was a key factor in our decision to invest in this technology, and we want to make sure things were working correctly there. So we'll give a couple of examples of that. We'll start with this sample that we've prepared. It's a multi-layer co-extruded system containing two different polymers. There's a cartoon shown in the upper right. These are polycarbonate and PMMA, where the alternate layer thicknesses are about a micron. And in the middle here we have a polished cross-section of the surface of this co-extruded layer. This is just an AFM height image. If you see my cursor, the vertical bands are alternating layers of the two polymers. The horizontal stuff is just a little bit of chatter due to the prep in the sample. So now we look at the infrared spectra of the two components. This is bulk IR spectra of polycarbonate at the top, PMMA below. And we see in the carbonyl stretch region for each of these molecules, polymers, we've got very good spectral resolution. That is, there's about a 50 wave number separation between the carbonyl stretch in these two polymers. If we put the AFM probe down on either alternate layers and collect a spectrum using the AFM-IR, in one case on one layer now we see a strong absorption that's coincident with that for the polycarbonate, 1778 wave numbers, and then in the adjacent layer we see a strong absorption due to the carbonyl from the neighboring PMMA. So clearly we can set the probe down and identify the alternate layers and which is which. And as Craig mentioned, now we can sit at either one of these absorption peaks and collect a map. We'll show that here. So we've got height imaging at the top, and then now we have maps representing the carbonyl from the polycarbonate in the middle and then from the PMMA below. These two maps can be pseudo-colored and overlaid, and that's shown in the upper right. And you can see we have very good edge resolution of these two immiscible systems, of these immiscible polymers. And if we take line sections across them and do some average profiling, we show that in the middle. And then we can look at this fall off of the edge either in the vertical height change or the spectral change for each of these resonances, we can estimate resolution at like 80% cutoff along that edge. And if we do that, we find that the iris spectral spatial resolution is about 50 nanometers, or in this case, it's about 4 pixels. So clearly, we're well below the 100 nanometers we anticipated. If you look a little bit more closely, we can blow up one of these pseudocolored maps and look at the pixel count at the edge, and in fact, it is about 4 pixels from low intensity to high intensity across the edge, which puts us clearly in the nanoscale regime for measurement. So that example, that's actually something that would be tractable by doing confocal Raman, albeit with many fewer pixels in each of those 2 polymer layers. So we thought we'd challenge the technique by preparing something with much finer layer thicknesses, and this was this multi-layer I mentioned earlier. And so this is a hybrid inorganic-organic layer. It's made by spin coating an organic polymer that has carbonyl functionality, and then a second layer, an inorganic with silicon-based silicon-based chemistry. And these were spun coated as alternate layers. Here's a picture of the stack in the lower left on silicon, and then a little cartoon again of the focused ion beam milling that was used to mill a 300 nanometer thick section that was plucked and then set down on the surface for us to look at. So if we start kind of again with a bulk analysis of this stack, we can do ATR from the top, so with ATR crystal at the top of the stack. And we see components of both polymers in this full spectrum. We see a carbonyl stretch at 1127 wave numbers, and then this SiO stretch at lower wave number. And we can again put the probe down in alternate layers and collect a spectrum in alternate layers based on this height image inset. And we see in one case we must be on the inorganic layer because we're seeing a strong response for this SiO stretch. And in the adjacent layer we see a stronger response in the carbonyl region. So clearly again we can identify which layer is which. We now sit on these 2 separate resonances and do some mapping as before. You can see we have the height image at the top, that due to the inorganic polymer in the middle, and that due to the organic polymer below. And if we do average profiles, we show those on the right. And so here we have a very smooth surface in this case from the fib polishing. It's only a few nanometers of texture. But clearly we can make out all 5 layers of each polymer in these average profiles. We can clearly see them. And we can do more than that if we can overlay them to see, in fact, that they are out of phase, one with the other, and make our resolution estimates in this case. These were taken at higher pixel resolution, and now we are able to see about 30 nanometer spatial resolution from the spectral mapping. The other thing that gets us excited about something like this is that we might more conventionally go after studying this kind of stack using those of you who are more familiar with conventional surface analysis. We could use, starting from the outside or left side in this case, and working in, we could use a sputter experiment, sputter depth profiling, and track using XPS or SIMS, X-ray-photoelectron spectroscopy, or secondary ion mass spectrometry to track these compositions. But we see it here directly in the morphology. And again, it's helpful to zoom in just to convince ourselves we aren't seeing things in a sense. So we can count about 10 pixels across each layer, and that's at a 10 by 10 nanometer pixel size. That's about 100 nanometers. So we see the modulation in intensity that corresponds to that resolution. So I think we're firmly convinced. We're seeing certainly better than 100 nanometer spatial resolution for the methodologies and systems that we used as test samples. Now we'll go to some real world examples and see how the technique plays out. And so we'll give you several examples of material systems and applications. The first one is a thermoset epoxy polyether blend, and this is used in the oil and gas industry. And let me go right to this. So this particular system, it develops a phase-separated morphology as it cures. And we prepare this system typically, again, as a cross-section using microtomy to get us our section thickness that we need for the AFM IR method. Here I'm showing you essentially more or less state-of-the-art mechanical measurements or property maps based on a technique, peak force QNM, which is from Bruker Instruments, but there are other AFM vendors have techniques to do this, and this gives us an idea of mechanical property variation in this morphology. And so we're well practiced here, and in this case, for instance, we see phase-separated domains that are a micron or submicron in size, and we see that these inclusions or spherical domains are about 7 times stiffer relative to the matrix, and this is based on calibrations and quantitative mechanical measurements. In this particular system, we always suppose that these phase-separated domains were epoxy-rich because we expect epoxy to be the more rigid component in this system. But we had no way of confirming that chemically until now with the AFM-IR. We also see here even some inclusions showing perhaps some compositional variation within the domains, and we'll talk about that in a minute too. So if we look at the IR spectra now of this morphology, here we have essentially the bulk IR shown at the top. We see components that we know come from, in the bulk, both of the separate components shown in green and purple below. So the epoxy, for instance, shows strong absorbances due to carbon-oxygen stretch and CH bending modes. The polyether shows strong carbon-oxygen carbon stretching that's absent in the ether itself, but of course when they're blended we see all 3 of these kind of features. So this helps us understand ahead of time what features or what frequencies we want to go after in mapping and studying this morphology. We can get spectra, of course, in each of the parts of the morphology. So if we look at these rigid domains, in fact we do see more CO stretch, CH bending associated with epoxy in those domains relative to the matrix, which is more polyether-rich based on the local spectra. And then, as before, we can go ahead and start mapping. Here's the field of view on the left, and showing you the height and top-down perspective. And then we map a couple of bands associated with the epoxy, and that lights up those small domains in the morphology relative to a band that lights up essentially the matrix polyether. And not only can we see the two different domains and something about their chemistry, we can make some estimates of compositional variation within the domains relative to the matrix. We see a clear enrichment of the epoxy feature based on the maps in these rigid domains, which we know are mechanically rigid. So we now are able to complete the story from the mechanics to the composition about what's going on in this phase-separated system. Here's an overlay map showing 2 of the bands associated with the epoxy, one with the polyether and the matrix in green. And even with the mapping, you see that within a particular particle, there is some modulation of composition. It's based on these intensity variations. So there's some finer scale compositional variation that would be more interesting to explore as well. We can take higher resolution maps, and when we do that, we find some interesting things. We start to see potentially enrichment of some of the polyether functionality at the circumference of these rigid domains, as well as what we think might be subsurface features that are not shown. For instance, these 2 locations, if you look in the height image, we don't really see any perturbation topographically at those locations, but spectroscopically we're picking something up. These might be buried domains below or something like that, but that's intriguing to us as we think about how deep we might be able to see with the technique. And then finally, let's look at spatial resolution, kind of revisit that question. We have a case in this morphology where we have both 2 rigid domains in very close proximity, so we can look at, do some average profiling across this region of the image, both in height and then in the IR response, and make estimates again from these step edges in terms of spatial resolution. And here we're seeing about 33 nanometers resolution in this very real world system. So again, confirming what we knew already from our test samples. So let's look at another phase-separated system. This is now from a different family of chemistries, polyurethanes. We're going to look at a chemical mechanical polishing pad. Morphology, they're used in conjunction with slurries for targeted removal of material from patterned silicon wafers in semiconductor processing. Here's a picture of what some of these pads look like in the upper right. Again, we'll start with what we know from mechanically mediated imaging in the AFM. This is, again, a polished, cryopolished cross-section. We have a phase-separated morphology again, and in this case, the phase separation is a result of the two types of chemistries in this polyurethane. We have more rigid isocyanate chemistries that we think lead to the harder domainal material, and then we have softer components associated with polyols or polyethers, like we'd seen before polyethers in the previous example. These react to form urethane linkages, and we think that enrichment of that urethane chemistry is likely present in these phase-separated domains. We again see it's a little different than the last system. You see now we have more diffuse boundaries in this case, and a much finer phase-separated size in this case. We're only 100 to 300 nanometers. So we again easily resolve this mechanically, and let's look what we can see spectroscopically. So in this case, here's the bulk IR, and you have AFM IR that's in a couple of different locations. And you can see in this case we've got very similar infrared spectra, at least at first glance, pretty much anywhere we look. And in this case we have to, it's a little bit more challenging. The compositional variation is a lot more subtle in this system. And so here we're actually going after variations in relative band intensities as a function of position, not necessarily nice separate and discrete absorbances that resolve in the morphology. But you can see, again, just reinforces the fact that the AFM-IR spectra look a lot like the bulk. You see that here very nicely. And if we go after something like urethane chemistry, where we look at hydrogen-bonded urethane, or at 1700 wave numbers or so, and scan over this cross-section, we now bring up these phase or harder segments, harder domains now are starting to light up in this morphology, and we can see that not with as good a signal noise as we've seen before, but clearly you can identify their locations. And this is now kind of a blow-up of that image just to convince you that some of the size of the domains we see are approaching 100 nanometers, and we are able to resolve them. We also can collect images and maps from some of the stronger absorbing locations in this material. For instance, if we go after things related to soft segment or ether linkages, we sort of get an inverted map now of those harder urethane, hydrogen bonded or free urethane locations in this morphology. And other strong absorbances that really are less well resolved in the mapping. One thing we clearly can identify, again, looking at the relative intensity in these maps, is that we see urethane enrichment in these harder domains. Again, kind of rounding out our understanding of both the chemistry and the mechanics and the morphology and the chemistry. Okay, so let's move on to another application. This is a multilayer film next, and this is for agricultural applications. It's a fumigant barrier film. It turns out that, generally we would use something like FTIR or Raman are sufficient to characterize a lot of these packaging multilayer systems, especially when the layers are very thick, although we've already talked about diffraction limited optics in those cases. And in many cases, when these films are made, the layers, especially barrier layers or glue or tie layers, can be very thin and less than a couple of microns thick. And that makes conventional methodologies nearly impossible to use. And so this is where something like AFM-IR can really shine. Some chemistries aren't necessarily accessible by, let's say, Raman for some of the chemistries that are used in some of the barrier layers. And so, again, another reason why AFM-IR is useful here. And I'd say, too, that there's a trend toward down-gauging these types of packaging and barrier types of films from several mils thick to something that's certainly sub 1 mil. And this particular example is one that's only 20 microns in total thickness. So this is an example of a commercial fumigant film shown in cross-section at the top using optical microscopy. Again, the total thickness is about about 20 microns. And we would typically use the conventional methods we use to characterize these kinds of films would be FTIR or ATIR on either side, and then FTIR through the entire film multi-layer stack. We try and understand also composition based on melting behavior using optical hot stage microscopy or DSC, and that can be used to make assignments of layer compositions. And in this example, the conclusion was that this was a three-layer film with an ABA structure, a central core consisting of EVOH, and then two flanking layers that were blends of two different types of polyethylene. So we took a thin section of this in cross-section. Before I get to that, let's just look at the spectra, excuse me. So we start, again, I mentioned bulk. In a bulk sense, we would do whole film transmission, and then these are now representative FTIR bulk spectra of both polyethylene and EVOH. And we can see that this fumigation film is really just a combination of these two materials. All of the spectral features are accounted for by just combining these two materials. And so now we know ahead of time that we can go after, let's say, unique spectral features in the mapping that might correspond to EVOH. We can look, for instance, the OH stretch, or maybe ether type of responses down here relative to CH2 modes associated with a polyethylene. And so here's what we find with the AFM-IR. We have a height image taken at low magnification that's of the cross-section that encompasses almost the entire thickness of the film. This is about 10 microns. And then here we're mapping CH2 modes associated with a polyolefin. And we can see a brighter response around the central core that its intensity then changes as we go further away from that core layer. And at a little higher mag, this is a little bit better resolved. We see what appears to be a higher density of CH2 immediately flanking this core and less so further away. When we map the CO stretch associated with the EVOH, we see that lights up nicely in the central layer and gives us a much better definition of that layer as well as its dimensions. We can see that quite clearly. So we kind of can put together a better story of what this composition and structure of this barrier film is. It really is now 5 layers and essentially looks like an ABCBA 5-layer structure, EVOH with a better definition of that core dimension. And then the 2 outer layers are polyolefins with varying ethylene content, probably different comonomer content. In the 2 adjacents relative to the outer 2 layers. And one final example I wanted to talk about is from water purification. This is some characterization of a very challenging sample, a reverse osmosis membrane. Before I show you the results, I have to talk a little bit about how this membrane is built, structured, and a little bit about its chemistry. The upper left cartoon shows the structure of one of these commercial RO membranes. The discriminating layer that does is responsible for the salt rejection in the layer is a very thin 200 nanometer layer of a polyamide material. We'll talk about that in a sec. It's supported on a porous polysulfone base, and that in turn is supported now on a PET, much thicker PET backing layer. The polyamide layer is made by interfacial polymerization, and that's a reaction of this aqueous phase containing metaphenyldiamine with an organic phase that consists of trimethyl chloride. It's reacted to form this amide linkage at the interface with pendant amine and carboxylic acid groups. And so when this actually forms, it doesn't form a nice continuous or smooth layer on top of the polysulfone backing. But if we look at this TEM image here, You can see this outer layer, this is the polyamide layer. It's actually far from smooth. It's highly reticulated and undercut in its morphology. And in this particular example, it's showing variation in thickness from, let's say, 90 nanometers to closer to 300 nanometers. So it's a very challenging material to characterize, especially by AFM. And our hope, of course, was to be able to use the AFM IR to understand local variations in chemistry at that top layer. So here's some of the results, and we like this example because it kind of addresses maybe some of the depth sensitivity questions about the methodology. If we take that full stack from the top down, that RO membrane, and measure several spectra, several positions, let's say along this line shown in the upper right in green, we get a collected an average spectrum shown here, and if we compare that to the bulk polysulfone spectrum, we see that most of these features that we see in the AFM IR are related to polysulfone, with some minor contributions due to that polyamide top layer. So we're seeing through the polyamide mostly to the sulfone below. We can remove that polyamide layer and lay it on a silicon wafer surface to laminate it, and then we take AFM IR spectra now, and now we get very nicely sharp peak, very well resolved spectra that are much more coincident with the bulk ATR that we would get off of that same polyamide layer that we collect separately. So it's interesting, in one case with the attack membrane, we tend to see through the polyamide. When we delaminate it, we see what we want to see, the polyamide functionality. And the sharpness of the spectra are very exciting to us because our hypothesis here is that if we start doing enough sampling across this morphology, we will see variations in intensity of relative bands associated with these amine, for instance, carboxylic acid groups that in some might aggregate to this envelope of responses that we see in the bulk. And so this gets us excited now that we are really thinking we're seeing very local chemistry, chemical responses in this methodology. So before I wrap up, I just wanted to maybe talk for a second about some of the things that are important in experimental setup for AFM IR. Since we're relying on this photothermal effect, the photothermal expansion, it's important that we have good thermal contact with the section that we cut to the substrate that it sits on. And that's easily achieved in the system set up with a beautiful, integrated optical top-down microscope and with low and high variable magnification that you can find those regions of a section where it's well attached. And that ensuring that gives us ultimate spatial resolution. And the other thing we have to be concerned about, and this is not limited to the AFM IR method but true in bulk, is the power that our laser sources we bring to the sample. They can be damaging to soft material, and so we have to, and this is an example of that epoxy thermoset where we had too much laser power during scanning, and you can see that the tip started to drag into the morphology a little bit. But there's a series of filters that one can apply to that to the laser to knock the intensity down, and so you can achieve that good balance between good signal to noise and damage threshold in materials. So at this point, I guess I'd like to stop and talk a little bit about our feelings about how this methodology works. We find it to be a very powerful technology for characterizing structure at the nanoscale. I think the bottom line is that in red there at the bottom is we really can see the composition now in the morphology, see the chemistry, where it goes. Is it going where we intend it to go? These are questions that we're always asked, and I think this is a very powerful capability that lets us get there. We see things that we can't see by conventional methodologies in the bulk. Of course, we are exceeding diffraction limits, so that gets the spatial resolution. And that spatial resolution is advertised, and you can see specking it against IR or Raman microscopy, we're doing much better. Craig alluded to the fact that these spectra can be used. They're strictly analogous to far-field spectra, and they can be searched in databases. We've done that. I didn't show that today, but I think Craig had some good demonstrations there already. And the exciting thing for us now is now actually doing compositional analysis, quantitative analysis at these scales, and we certainly can see small differences in composition, and I think kind of the next step is where do we go with being able to do this quantitatively. I hope I've shown you, at least in the polymer world, we're able to look at a variety of polymer chemistries, polymer morphologies, polymer structures with this methodology. And again, we see that chemistry and hopefully we see that it's going where we want it to go. So one quick slide, and it's probably the most important one, and that's the contributors who helped on the work. I just wanted to acknowledge quickly the 3D imaging team at Dow Chemical, who was involved with our evaluations and down selection of material systems to look at during our early evaluation of the capability, of the second generation capability. And then a couple of folks who helped with the fib prep that I talked about for that hybrid layer, and our colleagues at Nanoscale Instruments who gave us a lot of guidance and support during our early evaluation. So with that, I guess I'll stop, and thank you for your attention. And I think I'll turn it back to Craig maybe to moderate any questions.
Great, thank you very much, Greg. That was outstanding. We have a large number of questions. There was a question that, a couple of questions that you actually touched on, and maybe let me address this first. It was, could the local heating provoke material degradation, especially for biopolymers as PCl or PLA, and could it deform the material shape and induce peak shifting? And so let me address that first, then I'll turn it over to Greg. So as Greg said, we have sufficient laser power in the system that for many materials we can exceed the damage threshold. But we have two tools to accommodate that. One Greg talked about is we have a computer-controlled filter system. So there's a little drop-down menu where you can select how much of the beam power you want to go through to the sample, and you can select to less than 1% of the laser power, or up to full beam and a whole bunch of steps. And the additional tool that we have is that we can simultaneously monitor that contact resonance frequency while we're doing the AFM IR measurements. And so what tends to happen a lot of times, if you are using too much laser power such that you're damaging the sample, the material will soften, and we'll see a drop in that contact resonance frequency. And so then you can, having seen that, you can adjust the laser power to appropriately maximize the signal to noise. And Greg, is there anything you'd like to add to that?
No, other than, yeah, thanks for mentioning the contact frequency, because that we use that tool as well, and that's very helpful to be able to see that. That gives you a good real-time feel. As you go through an absorption, you can see that dramatically. So.
Okay, so we have a question about why do you microtome or fib samples now that you can do topside illumination?
I guess that's a very good question, because a lot of times in conventional AFM we'll just use block faces. We won't use sections for AFM. We find it's been our experience that the spatial resolution, especially when we start looking at that if you recall that multi-layer sample I first started talking about, the polycarbonate PMMA, as we get thicker and thicker, if we compare a section to a block face, we tend to see some pickup of the neighboring layer in the spectroscopy, and I think that's just because we're exciting such a bigger volume. So we like to keep the volume of interaction relatively small for better spatial resolution. So that's really kind of the driver there.
Right, and as a follow-up to that, so basically the infrared light can be absorbed through an extended depth of the sample. It depends on the strength of the absorption bands. And as Greg showed, you can get effects from buried layers or subsurface features depending on the geometry of the absorbing features. So if you have something below the surface that is, say, a spherical inclusion, you may be able to see the effect of it, down to a few diameters beneath the surface. But when it's deeper than that, you won't see it because the thermal expansion wave from that inclusion sort of dissipates by the time it gets to a surface. But if you have a very, very thick sample that's absorbing through a large depth, then you can get a thermal expansion from a larger area that can influence your spatial resolution. It also reduces the thermal or increases the thermal relaxation time, which can degrade the resolution. So for best resolution, thin samples are certainly the best. We have a question about how long does it take to record a 2D map, one of your absorption images.
Oh, okay, yeah, so that's a very good question. So let's see, real quickly. So low res, I guess low res takes about 10 minutes, which for those of you who do conventional AFM, that's very typical. For high res, I think I showed one example in that epoxy thermoset, polyether thermoset system where we did very high resolution mapping. That was closer to an hour per map.
We have a question about for AFM IR, what is the size affected by the IR beam? I assume that the beam size is much larger than the AFM tip. So yes, the laser, the infrared laser, is focused to a close to a diffraction limited spot, but that's still on the scale, as Greg mentioned, of many microns, a few tens of microns, depending on the wavelength. So the spot is measuring. I mean, the laser spot is much bigger than the AFM tip, but the reason that you achieve high spatial resolution is that the tip is measuring the thermal expansion locally. So if you have a small absorbing area, even though a large area is illuminated, only a small area may be thermally expanding if it's the only region that is absorbing. There was a question about suppose there's a high modulus mismatch between your two phases, for example, a composite. Would you expect a change in resolution in this case? Greg, would you like to comment on that?
Yeah, that's a good question. Since we're running, the experiment runs in contact mode at a fixed load across the sample, we expect to have more contact in a softer material than we would in a stiffer material, let's say in a heterogeneous morphology. We haven't studied that in any real depth yet. We do see effects, let's say, for very coarse morphologies if we're scanning, let's say, with large phase systems. I can't comment on it at a fine scale yet, but yes, you have to be a little bit concerned about deforming exceedingly soft material, but that's would require something that's probably 2 or 3 orders delta in modulus.
Yeah, one other thing I wanted to mention, we get a question, a related question often about, well, how do you compensate for differences in stiffness? Do differences in stiffness contribute to your spectra or to your image contrast? And in the case of spectra, the answer is no, because when you're sitting at one point and you are changing the wavelength of the laser, everything else in the system is staying constant. So the elastic modulus of the sample and the thermal expansion properties don't change as a function of wavelength. So when you change the wavelength, you get a spectrum that only reflects the the variation in the absorption as a function of wavelength. When you're doing IR imaging, the contrast can depend on these other factors like thermal expansion coefficient, elasticity, etc. But that's why we recommend doing ratiometric images, and Greg showed many examples of this, where you take an image at one absorption band and then you take an image at another absorption band, and when you ratio those, all of those other factors of thermal mechanical properties sort of divide out, and you're left again just with this ratio of absorption. Let's see, there was a question about were you able to quantify the circular epoxy domain thickness?
Oh, let's see. So, the thickness or diameter. I guess in that case, I mean, these are relatively polydispersed domains. So, I mean, we would typically do the sizing of those, not by this method, but we would do image analysis and look at, if I understand the question right, we would do image analysis and look at the distribution of shapes. And of course, the largest cross-section would be that of the largest diameter feature in that image, I guess, if that's the question.
Okay. We have a question about, have you looked at mineral-filled polymers and dark carbon-filled polymers, things like that? polymer carbon composites. Let me address that first. So, here at ANSYS, we have certainly looked at mineral-filled polymers, clay-filled nanocomposites, and there are interesting experiments that you can do looking at the how does the chemistry change, how does the stiffness change as you approach these mineral or other non-polymeric inclusions. On the carbon-filled, we can certainly do AFM IR measurements on carbon-filled materials. They have very strong IR absorption. One of the issues, though, is that carbon is a broadband absorber, and so the spectroscopic information can be less interesting. But we can certainly see the distribution of carbon particles through their IR absorption. Greg, is there anything you'd like to add on either of those?
No, I mean, yeah, I think that's been our experience, and we've certainly gotten good imaging on like silica-filled systems, looking at maybe hydration around some of the fillers. I mean, that kind of information is there. So, yeah.
We have a question about what's the best spatial resolution you obtained in AFM IR.
Yeah, so that lateral resolution is probably is about 30 nanometers. It's about the best we've seen. And again, some of that is tip related, and that's maybe one limitation, but that's about the best we've seen is 30.
Yeah, we've seen, say, 20 or 30 nanometers. The resolution can depend on the size of the objects and the thickness of the materials. And then with the SNOM technique that I mentioned briefly, if you're interested in even higher resolution, that can achieve sub 10 nanometer spatial resolution as well. You mentioned non-selective IR absorptions, and then your tip was gold coated. Can you expand on that?
Yeah, we don't want the tip contributing to the response, and so that's really basically what it is. We want which requires that the tips be coated with an IR reflective metal, and that helps. Then I don't know, Craig, you want to talk about maybe the focusing and so forth, but of the IR spot, but that ensures that we're getting the signal from the sample.
Right. So again, because the beam, the focused infrared spot is larger than the tip, you have the potential for light falling on the cantilever, light falling on the tip, as well as the sample. And so we want to minimize any background contributions from the tip and cantilever absorption. So we have an automatic technique that will scan the laser spot to find where the best AFM IR response is, that we will maximize the signal, minimize the background, and then having the tips gold coated, minimizing the infrared absorption of the cantilevers. There's a question that says, for Greg, in your epoxy polyether sample, I see the IR spectrum in the spherical domains also has features from the polyether. Does that mean the domain is a blend of the two materials, or do you get polyether signal from underneath the domain?
Yeah, that's a good question. I think at this point we haven't settled that question. I mean, I think we really expect it's likely due to compositional variation within the domain. And that's only supported because in that particular example we have also mechanical data from other imaging modes that tells us that there is compositional variation there. If we go back to kind of our standard materials that are multi-layers that have sharp interfaces, that's probably our best clue from a compositional standpoint. But and there we see relatively clean spectra from each of the components. But in that system, I think we think it's a compositional variation.
There's, by the way, a new paper on our website from a CIAC group in China working with Exxon, looking at some attempts at quantification where you see mixed spectra trying to determine the relative composition or relative concentration of different constituent components. There is a question about that I'll go ahead and answer. It says, how many lasers do you need to cover a typical IR spectrum from 4,000 to 650 inverse centimeters? So we have several different lasers available. We have one that, unfortunately, nothing that goes out to 650 inverse centimeters, but we have one that goes from 900 to 4,000 wave numbers. And that is based on what's called an OPO, an optical parametric oscillator. So that's our broadest band source. And then for the resonance enhanced technique, that uses a quantum cascade based laser that has a narrower tuning range, but then it allows higher sensitivity measurements, and that goes from roughly about 900 to 1,800 inverse centimeters, so there's some flexibility in the choice of the individual QCL modules. We have a question about, can you detect local changes or spatial variations in thermal conductivity? And we do have a complementary technique that I didn't mention called scanning thermal analysis, and in this case we use these heated AFM tips, and so we will heat them to a set temperature and then scan over the surface, and we can measure the change in basically heat transfer into the sample. And so areas of high thermal conductivity cause the tip temperature to go down. Areas of low thermal conductivity maintain the higher temperature, so you can at least get a qualitative measurement of the thermal conductivity with those. There's an instrumentation question. Are you getting these spectra in some sort of vacuum, or is it in air? All of these measurements are happily done ambient, so there's no special sample environment that is required to do the measurements. Let's see. There's a question about when comparing the bulk IR spectra to the nanoscale IR spectra, the peaks tend to shift. How would you decide if the peak seen in the nanoscale is still the same as the peak in the bulk material? So I think Greg and I will both answer that. So we've done some very careful measurements on highly homogeneous materials, and we see extremely good correlation between the peak positions in AFM-IR and FTIR, down to fraction of a wave number agreement. And the reason that they agree is that we're measuring the same fundamental property. We're measuring the absorption coefficient, whereas some other techniques like the SNOM technique is measuring something indirectly like the scattering, which can have a more complex dependence on the sample properties. But in the case of AFM-IR, we're directly measuring the absorption coefficient. So for homogeneous materials, there are not peak shifts. Now, for heterogeneous materials, there can be very interesting peak shifts, and that's something that that we use to characterize things like
local crystallinity or orientation effects. Because remember, these bulk spectra that you're seeing, you're taking a spectrum over a large area where it's averaging over all the molecular orientations, and the peaks tend to get broadened. And so for nanoscale spectra, you are looking locally, and so you can see much narrower peaks because you're looking at a specific orientation of molecules or a specific phase of molecules. And Greg, would you like to add anything to that?
No, I think you answered it well. And that latter point was very exciting to us. Those subtle shifts in either intensity or position due to local bonding interactions. That's where all the excitement is going to be here, I think. I mean, yeah, and certainly echoing what you said on bulk samples. Exactly. There's no reconstruction of the spectrum. It's direct. Yeah.
We also have seen really interesting, like in some of these multi-layer films, we'll look at the the peak center and the peak width as we're going across the interface, and you can get some really interesting information about the interface chemistry from what's going on with those peaks. We have a couple of questions about price range and the instruments, and we'll be happy to contact you offline to talk about that. A lot of it depends on the specifics of the application and laser source, etc. So there's a question about what type of substrates do you recommend? So Greg, can you comment on the substrates you typically use for your measurements?
Yeah, we've been using you can use something like gold-coated quartz is a gold mirror basically, zinc selenide, zinc sulfide, IR transparent supports, and those are common ones that we would use.
Yeah, and in general you want a substrate that is either IR transmissive or IR reflective but not IR absorptive. Let's see, you mentioned thermal conductivity is critical, and then the person asks, what tape or adhesive do you use to adhere the cross-section to the substrate? So, tape or adhesives are not normally used, but maybe, Greg, you can talk a little bit more about how you do the sample preparation, how you adhere the sample to the substrate.
Yeah, so in the microtomy experiment, these are simply either at room temperature, they're plucked and just laid down on the surface. We may, depending on the materials, we may use a drop of water to assist in this section laying flat. As that drop dries, it will pull it down to the surface. We kind of get that naturally in the cryo case because we maybe some water condensing as it warms up and pulling the sections down. But we don't use any. Absolutely right. We do avoid using any third-party agents there, adhesives or the like. And so it may take us a few tries to get. Typically we'll lay several sections down on a substrate and search them optically on the stage and then pick the ones that look the best.
Yeah, there's another related question. You mentioned that the thin film has to be properly mounted on a substrate. Is it for heat dissipation? How do you stabilize the films on a substrate? So, typically if we're doing a microtome film, we're going to transfer to the substrate, to the zinc selenide or sulfide or gold-coated surface, and where typically what happens is either you get a good bond or you don't, and so in the areas that you don't have a good bond, you'll see a little bubble. You can see it very clearly in the optical microscope, and so you avoid those regions. And anywhere you don't see a bubble, then there generally is good adhesion between the microtome section and the underlying substrate.
Yeah.
Let's see, there was a question about did you take, this is on slide 38, did you take a transmission spectrum of the delaminated membrane with conventional FTIR microscopy?
Well, yes, for that one, let's see, that was, I think, done by ATR on the isolated layer. Yes, and that's actually what's shown on 38. Yeah, this is done by ATR of the delaminated membrane.
There was one about AFM-IR and FTIR basically measure the same thing, but the detection techniques are different, so I guess the spectra can be different. What are the possible reasons for the difference? And so, yeah, I would say most of the reasons for the differences between AFM-IR and FTIR is that AFM-IR is measuring something locally. FTIR is measuring over an average. So it's averaging a large region, you're getting sort of the ensemble response where the AFM-IR is measuring very locally and is therefore sensitive to local variations in the chemistry. That's all the questions that we'll take today. I'd like to thank you all very much for your participation. Thank you so much, Greg, for the great webinar. That was really outstanding, and wish everybody a great day. Thanks so much.
Thank you.